Thanks everyone for coming here today, and thanks to everyone who's joining on Zoom. Our speaker today is Dr. Jeff Maki, who has expertise in a wide range of fields, ranging from transport to non-equilibrium dynamics of quantum many-body systems. He completed his PhD at the University of British Columbia under Professor Fei Zhou, and then proceeded to go global with a number of postdoctoral positions. He has worked with Professor Shizhong Zhang at the University of Hong Kong, on transport of finite range interactions. He's also worked with Tillman Enns at the University of Heidelberg while visiting there on the transport of P-wave interacting Fermi gases. Very recently, he's finished a postdoctoral position at the Pitaevskii BEC Center in Trento, Italy, under Professors Alberto Biella and Sandro Chingari on the non-equilibrium physics of open quantum systems. Starting in October, he'll be expanding his expertise into the study of quantum criticality in open systems under Professor Oded Zilberberg at the University of Konstanz, Germany. Dr. Maki will be in Toronto today and tomorrow, so hopefully you have the chance to pick his brain while you still can. Today, he'll be speaking to us about anomalous transport in 2D Fermi liquids.
Yes. I'll say the rest of it. The odd even effect and damping the quadrupole mode in atomic gases. Yeah. So thank you very much for the lovely introduction.
And with that, please join me in welcoming Jeff Maki to Toronto.
Thank you. Yes, thank you very much. This is my second time in Toronto, but really the first time I got to explore it and actually to come to the university. So I'm very excited to be here to share with you, my recent result that I submitted to the archive about anomalous transports in 2D Fermi liquids, the odd-even effect and the damping of quadrupole modes in atomic gases. Now, this is work that I didn't do by myself. I had two collaborators, Johannes Hoffmann at the University of Gothenburg and Ulf Gran at Chalmers University, both of which are not only in the same city of Gothenburg, Sweden, but their two university physics departments share the same building. So it's a fun place to go to do physics. They are supported by the Swedish Research Council, as well as this national academic infrastructure for supercomputing in Sweden. I myself, as Kevin mentioned, was a member of the Pitaevskii BEC Center, which is a branch of this Consiglio Nazionale della Ricerca and the Istituto Nazionale di Ottica. These are national research agencies in Italy. I'm sorry that this randomly appeared again. Let me move that out of the way. Hide float meetings. Thank you. Yeah, the Pitaevskii BEC Center is also attached to this University of Trento and supported by the province of Trento, which has this very cool black eagle logo that you see here. Okay, so I would like to begin with an outline of this talk. First, I'll review Fermi liquid theory. This is the theory to describe systems of strongly interacting fermions, or just interacting fermions at very low temperatures in terms of weakly interacting quasi-particles. From there, we'll focus in on two-dimensional Fermi liquids, and I'll show you that there can be this thing called the odd-even effect that can emerge. And this is essentially, there are two different types of quasi-particle scattering that can occur in 2D Fermi liquids, and they can have parametrically different scattering rates. And it turns out that this was analyzed in the context of condensed matter physics, and in particular, electron hydrodynamics of two-dimensional materials. And there, people found that there could be an anomaly due to this odd-even effect in the transport. In particular, you can have a scale-dependent shear viscosity, which can be then measured in things like how current flows through a pipe or in conductivity experiments. However, it turns out that this odd-even effect is very general and can even apply to cold atoms. I'm a cold atom theorist. It turns out that cold atoms is also a great place to study this because atomic gas experiments have a lot of control over them. And in particular, we can do something that's very difficult to do in condensed matter platforms, which is change the interactions. And actually, we can use that to tune this odd-even effect. So not only can we study if it's there in atomic gases, but how it is actually destroyed as well with interaction strength. And in particular, I'll show that actually cold gases gives us a nice physical observable to study this odd-even effect, namely the damping of the quadrupole mode. The quadrupole mode is just a collective mode of a Fermi gas placed in a harmonic trap. Essentially, the gas is expanding and compressing in an anisotropic fashion. And the damping rate actually depends on the shear viscosity spectral function, which acquires this scale-dependent anomaly when there's an odd-even effect. So really, this can lead to an anomalous enhancement of the damping rate compared to hydrodynamic predictions, and this would be the smoking gun for cold atom experiments of this effect. Then I would like to actually show you calculations that I did with my collaborators. We used a Fermi liquid kinetic theory to actually calculate the shear viscosity spectral function, and I'll show you results about, we actually do indeed see an anomalous enhancement of the damping of this quadrupole mode. And then we can conclude for the day. So let's begin with Fermi liquid theory. Fermi liquid theory was developed in the 1950s by Landau, and he was inspired by this observation that interacting systems of fermions at low temperatures can have a well-defined Fermi surface and a Fermi sea. He also reasoned that essentially excitations above that Fermi sea would be described similar to what you would see in non-interacting systems. There would be particles and holes, which he calls quasi-particles. The best description I've seen of what a quasi-particle is comes from this book by Matic. So you can view a real particle kind of like a horse running down a road. Now, if it's a dirty road, the horse will naturally kick up a cloud of dust. Now, it is an extremely difficult problem to try to track the motion of the horse and every particle of dust that it kicked up. Rather, you can treat the whole object, the cloud of dust and the horse, as a composite object, which is our quasi-horse here. So this is a much simpler thing to imagine. Now, in the context of fermions, this is our fermionic atom or electron. And essentially, by moving through the system, it will perturb all the other fermionic atoms or electrons in the environment. And essentially, the dressing due to this mutual interactions will lead to this quasi-particle. So that's actually what's shown here. Quasi-particles are dressed by the interactions of other particles. With first term in this dispersion is just the bare kinetic energy. So it's just the momentum squared divided by twice the mass. I will denote the mass here by this m star for reasons that will make sense on the next slide. And the second term is the energy cost that the particle acquires due to disturbing the environment. So here, this FPP prime is some interaction energy between two quasi-particles with momentum P and P prime. And this delta NP prime is the change in the distribution function of particles with momentum P prime. So again, the idea is that if everything is equilibrium, there's no energy cost. But when a particle or quasi-particle comes flying through, it will push on the others, and that costs energy, which is why you see this term here. Now, it turns out the benefit of Fermi liquid theory is that a large number of the thermodynamics can be described in terms of their non-interacting counterparts, but multiplied by some interaction-dependent constant, which we call these Landau parameters. They're defined as this capital FPP prime, which is essentially that lowercase fpp prime multiplied by the density of states at the Fermi surface. Now, for isotropic systems, we can expand this in terms of angular harmonics. We will be focused here on the case of two dimensions, where the angular harmonics are just complex exponentials. So here, m is our angular momentum quantum number, and theta p is just the angle that the momentum vector p makes with some reference axis. But the key thing to note is that this Fm tells us about the interaction energy in a finite angular momentum sector. And as advertised, here's a number of physically relevant quantities that actually just depend on a few of these Landau parameters. So for example, we can have the effective mass, m star, again, not to be confused with angular momentum m. It's related to the bare mass by 1 plus F1. Similarly, the compressibility, which is related to how the pressure changes when we change the volume of the gas, is related to its non-interacting value multiplied by this ratio of F1 plus F0 divided by 1 plus F1. Similarly, the specific heat, how the energy changes with temperature, is related to its non-interacting value, but multiplied by this 1 plus F1 here. So really, we can describe the thermodynamics of Fermi gases, interacting Fermi gases, using essentially some non-interacting physics with interaction-dependent coupling constants. And actually, this has been a very successful program. In fact, one of the first successes was in liquid helium-3, which is a very strongly interacting normal Fermi gas. And actually here I wanted to show you this table from a book by Baim and Pethick on Landau Fermi liquid theory. So here I would like to draw your attention to these first three rows, which are exactly the quantities that I told you before. We have the effective mass, F0 and F1. Now, a lot of experiments actually were able to extract these quantities. So they found good agreement, basically, with Fermi liquid theory. And here you can see that at 0 bar, we have some very strong values of these interaction parameters. So in other words, we see the effective mass is almost 3 times as large as the bare mass. This F0, which for a non-interacting gas would be 0, is 9. And similarly, F1 is 5. You know, for a weakly interacting gas, we might expect these things to be small, but these are actually very large. So this is a signature of the fact that we have a strongly interacting system. But nevertheless, we can use Fermi liquid theory to describe kind of the thermodynamic properties thereof. Yeah.
Did I catch it wrong, or didn't you say that m star over m is given by 1 plus f1? It looks like this disagrees with Fermi liquid theory.
Yeah, I should check with that one because you're absolutely right. In principle, it should be 1 plus f1, which was guaranteed by the Gaussian invariance. But I need to check with this one in particular, because I also know that there's a little caveat here about the thermal conductivity, which I think is a little bit off for Fermi liquid theory. So there might be some disagreements. But I believe that I'll have to think about that a little bit more for the exact case of superfluid helium-3. Yeah.
But superfluid helium-3 is believed to be a good test case.
Exactly. But I do know that there is some disagreements. Like, for example, this, I was reading about this recently, this gray walls measurement of the thermal conductivity has this weird log business, and that there is some disagreement in some quantities. So, but you're absolutely right about that. But continue on. Actually, Fermi liquid theory can apply to other systems. For example, I found this phase diagram for, let's say, strongly interacting high TC materials. Yes, but at low temperatures here, this can be described in terms of Fermi liquid theory when you have a normal metal phase. Similarly, Fermi liquid theory can be useful for describing things like atomic gases. As long as we have a normal Fermi gas at low temperatures, it has a well-defined Fermi surface, and we can describe it in terms of Fermi liquid theory. In fact, there was a recent paper from Nir Navan's group, which I recommend to my atomic gas colleagues in the crowd to read. There, they actually measured the density response function. So this is the real part and imaginary part of the density response function for an interacting Fermi gas at low temperatures. That's what's shown by these different colored dots, which are essentially due to 2 different interaction strengths. These theory lines actually are different flavors for Fermi liquid theory and how to capture the quasi-particle scattering rate. But you can see that it fits the data quite well. So also atomic gases are a great place to study this physics. Now, the one thing I haven't told you is why Fermi liquid theory works so well. And the answer is that scattering between quasi-particles is suppressed at low temperatures. The simplest way to show that is to consider 2 equal and opposite points of the Fermi surface and to allow them to scatter. Now, it turns out that it can only scatter in this red ring, which is the thermally broadened Fermi surface. So particles in here cannot scatter because there's Pauli blocking. And outside, there's nothing. So really only scattering can occur at this Fermi surface. Now, if one does a Fermi's golden rule-like calculation, one can show that the scattering rate of quasi-particles scales like the temperature squared divided by the chemical potential, which is nothing more than the Fermi energy. So as advertised, when T goes to 0, the scattering rate goes to 0. And as a result, the lifetime of these quasi-particles becomes exceptionally long-lived. But it turns out in 2D, this analysis is a little bit too naive. In fact, there are different types of quasi-particle scatterings that can be present, and they can have drastically different lifetimes. Now, the best way to show this to you is actually to change our language to deformations of the Fermi surface. And you can think of that easily. These 2 things are related. If I take a quasi-particle and I put it, like, let's say here, I'm changing the shape of the Fermi surface. But the reason I like talking about these deformations is that you can clearly see that they come in 2 flavors. We have even parity, which is shown here in the blue, and odd parity, which is shown here in the orange. Now, it turns out that this form of quasi-particle scattering, which we just discussed, only applies to the even deformations of the Fermi surface. So rather, the relaxation rate of this guy here is related to this even quasi-particle scattering, and the relaxation rate goes like temperature squared divided by the chemical potential. And this is because when this type of scattering actually positively correlates opposite points of the Fermi surface together. To relax these odd parity modes, you need many small angle scatterings. But this turns out to actually go by a different process, which is shown here. So the small angle scattering is actually suppressed. In fact, the only angle you can change by is about the order of T over the Fermi energy. And one can show using the same Fermi's golden rule calculation that the odd parity relaxation rate for this guy scales like temperature to the 4th power divided by the Fermi energy cubed. Yes?
These quasi-particles, they have anything to do with like the quasi-electrons of Fermi liquid theory, or are you saying they're the same or completely?
Well, I'm saying that so in the Fermi liquid theory, you can expand in terms of the essentially the change in the distribution function, which tells you about adding extra quasi-particles at different momenta. But you can, if you're very focused in on the area around the Fermi surface, you can kind of view that as deformations of the Fermi surface. So again, like if you think if I put a particle here, I've changed the shape of the Fermi surface as a result. Does that make sense? So, but the reason I like this is that because you can see that you can kind of decompose those two into, let's say, even and odd parity harmonics. Yeah. Does that kind of answer your question, or is it a little? Okay. It's a little, maybe it's a little tricky, but yeah.
Sometimes people bosonize Fermi surfaces by considering like, the boson is a bosonic field is like the deformation of the Fermi surface. Is that?
No, I don't think that's not what we're doing. It's more like the fact that the distribution function of the quasi-particles, which it's like a Fermi-Dirac distribution with a small bit, and a small bit can be expanded in terms of spherical harmonics, which are these guys. So you can either talk about physically, I add quasi-particles at this momenta or this momenta, or I can think about kind of doing it this way in terms of I'm adding spherical harmonics. Sorry, I bumped the microphone.
This is very relaxing differently in 2D. Is this also true in 3D as well? Or is that...
Don't know, but I would like to, I'll go, that is a good question. The answer probably is no, as I will discuss on the next slide, but I'll just give the punchline away now, which is that really this discussion here is really about the kinematics of 2D. So you have a 2D Fermi surface, you have polyblocking on the inside, you're only allowed to scatter in this ring, and then that naturally leads to this, I'll get to the punchline. We call this the odd-even effect because even parity deformations and odd parity deformations can now relax at parametrically different rates.
What is that? I mean, what's that usage parametrically?
Temperature. So as both of these go to 0, they scale differently with temperature. So as a result, I'll continue on from this point. That's a good, thank you for that. Essentially, as long as T goes to 0, both of these rates are going to go to 0. But at fixed temperature, this relaxation rate will always be much larger than this one. Because it vanishes, assuming this is a small quantity, it vanishes with a higher power of temperature.
And so far, you're not considering collisions between one even and one odd.
I think because this is a rotationally invariant problem, there's usually we're thinking about, when you think about deformations, you're thinking more about, let's say, pairs of quasi-particles. So like, in other words, this scattering has even, so it's more, I would say, this is kind of related to your question, which is that we, instead of working with quasi-particles, we talk about different ways we can, change the shape of the Fermi surface, and they'll each relax at a different rate due to different types of quasi-particle scattering, so either A or B, and there should not be any kind of crosstalk because of conserved angular momenta. So you either, it's like each of these are kind of two independent sets.
Total angular momentum of the pair of quasi-particles that collide.
It should be the total pair of the pair.
So then I was thinking, as soon as you create lots of quasi-particles, unless they're all even, they're always going to be
some of this, yeah.
there are always going to be, sorry, there'll always be combinations that are even, right? If two odds collide, it'll be even.
Yeah.
So there's always a fast channel.
There's always a fast channel. That is correct. But the key thing about this talk is to ascertain if there is new physics due to this odd even effect that is tied to this odd channel here. So continuing on. So the key thing that about this that's very interesting that one can envision is that there's a new dynamical regime that emerges. So let's consider driving our Fermi gas or system with an external probe or some external field that changes on a time scale, which is lowercase t. Now one can envision this new regime, which is called the tomographic limit, where the time scale at which we drive the system is much larger than the relaxation time of these even parity modes, so this fast channel, but much slower than the odd parity relaxation time. So essentially we perturb the system, then these even parity modes can quickly relax to some equilibrium value, but these odd parity modes are stuck. And this should be compared to, let's say, traditional transport regimes like hydrodynamics, where both of these modes can relax after we perturb them, and the collisionless regime, where they're both stuck. So really, this tomographic limit essentially has hydrodynamic even parity modes and collisionless odd parity ones. Now, this is very interesting, but coming back to the question that you posed, are there probes that depend on these odd parity modes? Because they're the ones that can become long-lived at very low temperatures. And in fact, this was actually answered in the context of condensed matter physics in electron hydrodynamics by Leonid Levitov, looking at basically the hydrodynamic flow of two-dimensional materials. And there he found that transverse probes of the dynamics at finite momenta depend on these odd parity modes and can develop anomalies due to this odd-even effect. In particular, if one examines the shear viscosity spectral function, so this is really the response of a fluid to a transverse velocity field. So in other words, you have a slowly changing velocity field in one direction, but it's oriented transverse-wise. If you take the low frequency momentum limit, what they found was that naively in the Fermi liquid theory, you would get this result. The shear viscosity depends on the density, the Fermi momentum, the Fermi velocity, and this constant gamma eta, which is a constant of unit frequency that tells you about the interactions between the quasi-particles. But when you have the odd-even effect, it becomes momentum dependent. In fact, there's a new length scale that emerges, which is CQIQC, which depends on the Fermi velocity and the relaxation rates of both the odd and even deformations of the Fermi surface. Now, when Q times CQIQC is very large, you can see that the shear viscosity actually in this low momentum, when I say low momentum, still assuming Q times B is much larger than 1, you can see that there's a 1 over Q dependence that will appear here. And this turns out to be very important in studying things like fluid flowing in a pipe or conductivity. So if you actually open up the shear viscosity on Wikipedia, the first thing you see is that it tells you that if you have fluid flowing down a pipe, a shear viscosity tells you about the magnitude of the velocity field and how it changes with this vertical direction y. Okay. Now, because of I should actually mention that this is what's given by this blue line here in this overall plot. Now, in this tomographic limit, there's this anomalous momentum dependence, which actually is set by the width of the pipe. So really, Q here becomes 1 over W. And as a result, there will actually be a change in the fluid profile shown by these red and orange lines. Now, these red and orange lines correspond to two different flavors of this, let's say, tomographic physics. But the key thing to note is that they differ in comparison to the hydrodynamic prediction. Now, this is all well and good, but as an atomic gas theorist, let me make some possibly incorrect claims about condensed matter physicists, which you can correct me on. Understanding the shear viscosity in electron hydrodynamics is a little bit more challenging. First things, you have things like impurities and other things which obscure the hydrodynamic limit. And also you have to generally infer the shear viscosity from some form of quantity like the non-local current measurements. There's not really a direct way to just probe it. Now, that being said, there was a paper that just appeared on the archive less than a month ago from Corey Dean's group about the observation of the shear viscosity in Corbino rings of monolayer and bilayer graphene. There, they actually were able to extract this kinematic velocity with viscosity, which is also unfortunately called nu. Here it is the ratio of the shear viscosity to the density. And the idea was that in this tomographic limit, because of the odd-even effect, this kinematic viscosity should decay like 1 over temperature, which is clearly what they see for monolayer graphene and bilayer graphene. But I should emphasize that this is extremely cutting edge. This, again, just came out a month ago. So, I mean, my collaborators and I were inspired by previous calculations from several years prior, but we're trying to find a better platform, or at least another platform, to study this odd-even effect. Now, of course, I'm an atomic gas theorist, so the place I go is atomic gases. And it turns out that this odd-even effect is very general. As I mentioned previously, it only depends on a few things. First, we need to have a Fermi gas at very low temperatures, because then we have a well-defined Fermi surface. And essentially that coupled with polyblocking gives you everything you need. The only other caveat is that the system must be normal. In atomic gases, we can make, superfluids and superconductors out of fermions. We do not want that. It has to be in its normal phase. It doesn't really depend on the type of interaction you have in your system. In fact, that's exactly what we showed here. This is a figure from our manuscript. Essentially, this is the relaxation rate for either these even parity deformations of the Fermi surface, as shown by the solid lines, or the odd parity ones, shown by the dashed lines. Now, these 3 different colors, I can get into them maybe after the talk, but suffice to say, they are different approximations for the scattering between 2 different quasiparticles. Now, independent of the approximation we use, we find qualitatively similar physics. When beta mu, which is the chemical potential divided by the temperature, is very small, we don't see any evidence of the odd-even effect. In fact, the even and odd relaxation rates are about the same order of magnitude. If beta mu is very positive, we actually see that they start to separate, and we can actually obtain the same scalings I told you about previously, which is that the even parity deformations go down like t squared, whereas the odd parity ones drop like t to the 4th. But again, it does not really depend on the interaction strength. Now, what's interestingly enough is that if we look at about beta mu's on the order of 10, or even better, maybe about 11 or so, we can see that, or 20, I should say, we can see that the odd parity and even parity modes are starting to diverge. Now, this is important because if we have a weakly interacting Fermi gas, beta mu of about 10 corresponds to a temperature which is about, let's say, 0.1 times the Fermi temperature. And this is achievable in atomic gas experiments. So really, we're saying that this is perfect for cold atoms because we can actually achieve the temperatures needed to see this odd-even effect. But what's better about cold gases is that we can actually change the interaction strengths with the system. So, and we can use that to change the chemical potential. That's actually what's shown here. This is an experiment from Selim Yilkum's group at the University of Heidelberg. There, they examined the low energy equation of state of a 2-dimensional Fermi gas. So this is the chemical potential in units of the Fermi energy. And this horizontal axis is essentially the interaction strength. I should note that during this whole process, the temperature is roughly fixed to be about 0.1. So that's why I mentioned beta mu about 10. So when this log, I should mention here that this log KFA, KF is our Fermi wave number, and A is a parameter that describes our interaction strength, which is called the 2-dimensional scattering length. This quantity is related to the dimensionless interaction strength through this formula. So when log KFA is positive, this G tilde is negative. We have a weak attractive interaction. And at very low temperatures, we'll have a well-defined Fermi surface, and the beta mu will actually be positive. So this is what we want to see for this odd-even effect. However, when the interaction becomes strongly attractive, or when log KFA is actually negative, which corresponds to a repulsive interaction, the fermions can form diatomic molecules, which are bosons. at very low temperatures, those bosons will then condense into a BEC. But the key point is that we don't expect there to be a Fermi surface. So in reality, this area, we expect the odd-even effect to occur, but we also have access to basically being able to destroy it at will by just changing the interaction strength, which is something that's very easy to do in atomic gas experiments.
But you don't want to be below the BCS transition.
Yeah, that you want to avoid. So I guess there is essentially a bottom limit. We can't go too cold because then you don't want you want the system to be normal, but you also don't want it too hot because you want the well-defined Fermi surface. That's correct. So there definitely, if we talk to experimentalists, there definitely needs to be a balancing of these two effects in order to maximize the chances of seeing this. But the one thing I haven't told you yet is that what experimental probe can actually observe this odd-even effect. And like electron hydrodynamics, we're going to look for transverse probes of the system. And there's one very famous transverse probe in atomic gases, which is this quadrupole collective mode. So that's exactly what's shown here. Essentially, the gas is expanding and contracting in an anisotropic fashion. So here, these two green lines are different, essentially the spatial profile of the gas at two different times. Now, the black dashed line is our equilibrium position. So the collective mode is oscillating about this equilibrium size. And we assume at low temperatures that the density of the gas follows this Thomas Fermi profile. It's an inverted parabola with this length scale r, which is called the Thomas Fermi radius. This Thomas Fermi radius depends on the trapping frequency and the number of atoms. In particular, if we have a very shallow trap, r becomes bigger. Tighter trap, r becomes smaller. Now, the key thing to note is that in the hydrodynamic limit, the frequency of this quadrupole mode is square root 2 times the harmonic trap frequency. But the damping rate actually depends on the shear viscosity spectral function following this relationship. So gamma q is our damping rate. It depends on this quantity in E kin q, which is the kinetic energy associated with the following quadrupole velocity field. Now, as you can see that if I take this ansatz and plug it in here, this is just a number. So really, the core of this formula is we have the spatial average of the shear viscosity spectral function evaluated at a finite frequency, which is set by this omega q, and a local position r. Now, in this talk, we're going to encode all the effects or the presence of this odd-even effect in terms of this anomalous shear viscosity. So we're really looking for some kind of formula that can interpolate between, let's say, the conventional predictions of hydrodynamics, as well as this new tomographic limit. And to do that, we kind of make a similar argument to the fluid flowing in a pipe. We note that if we look at the magnitude of this quadrupolar current, well, it vanishes at the center of a cloud. And if we take a cut along the radial direction, it kind of has the same thing. There's a maximum somewhere near the center, and then it vanishes on the two sides. Over here, it vanishes because there's essentially no flow at the center, and out here, you have no more atoms. So there you go. So really so this is quite nice. And the second observation that we had was that if we average over the inhomogeneous density, then what we're really going to do is we're going to select out a momentum mode of this shear viscosity spectral function at which this current profile varies. And that is going to be essentially 1 over r. So the crux of this argument is that essentially, at the end of the day, the damping rate of the quadrupole collective mode is related to the shear viscosity spectral function at finite frequency and finite momenta, where the frequency is set by the harmonic trapping potential, and the momenta is set by both the trapping potential and the number of atoms. As advertised, this interpolates between the two limits. So in the hydrodynamic limit, we simply set the momentum as here is equal to 0. This can be achieved for having extremely flat traps, so homogeneous space. Also, it can be achieved by having very large atom numbers. So then everything locally looks homogeneous. However, if Q becomes, let's say, important, and Q times Xi or over Kf is on the order of 1, we expect the odd-even effect to then be present. So this is all well and good. So now we have a physical prediction that we claim that the damping rate of these quadrupole modes is affected by this odd-even effect. The next part, unfortunately, is the technical part. I want to briefly tell you about how we actually calculate the shear viscosity spectral function and the damping rate of this quadrupole mode. I promise that this will only be about 3 or 4 slides, and then it should be quickly over. Yeah, I know there's some experimentalists here. All right, so we're interested in this quantity, the shear viscosity spectral function at finite frequency and momenta. We calculate that using kinetic theory for Fermi liquids. So really what we're doing is we're looking at the dynamics of the distribution function of quasi-particles with momentum p. And what I haven't shown you here is that this is local in space and time. Okay. Now this left-hand term is what's called the streaming term. And it basically describes the kinetics of these quasi-particles. So here, this first term is telling you the fact that if at this point in space, quasi-particles have a finite momentum p, so therefore they're moving out of that position. Similarly, the second term tells you that the fact that at this point in space, the quasi-particles, they feel an external force. And in particular, we have 2 external force terms. The first term here is due to an external velocity field. This is what we use to calculate the shear viscosity. And the second one is let's say a Fermi liquid force, and it's due to the fact that, again, the Fermi liquids are not quasi-particles are not completely independent, but when they move through the system, they will disturb other quasi-particles and have to pay an energy cost. So this gives you a second force acting on these quasi-particles. This last piece is what's known as the collision integral, and it describes 2-body scattering of quasi-particles. It's this very long formula, but I promise that it's actually relatively simple. We have the matrix element that tells us about the scattering between 2 quasi-particles. These delta functions ensure conservation of energy and momenta. And this last bit basically tells you about the phase space available for scattering. So this is really Fermi's golden rule right here. But one of the benefits of Fermi liquid theory is that we can actually describe the matrix element coupling 2 quasi-particles, or describing the scattering of 2 quasi-particles, sorry, in terms of the Fermi liquid parameters here, in particular F0. Now, coming back to the beginning of the talk, I said that these Landau Fermi liquid parameters can actually be extracted from thermodynamic quantities. And in particular, for quantum gases, we assume we have S-wave or isotropic interactions. So we throw away any Landau parameter with higher angular momenta. This is just a first-order approximation. And now we're just left with F0, which, as I mentioned before, can be extracted from the compressibility. But the compressibility itself is related to the change in the chemical potential with respect to the density. That's exactly what was provided here by this lovely experiment. So in fact, we can actually do what I believe is a very nice thing. Instead of using some approximation to describe the scattering between quasi-particles, I can actually use information from the experiment to basically encode or this single parameter into our Fermi kinetic theory. So this is, I would say, is a very nice thing. And again, it describes, once we have this, we have our total kinetic theory just down set. This was essentially one of our only free parameters. The next thing we have to do is solve the kinetic theory. And we do that by linearizing it. So we assume that the distribution function of quasi-particles is roughly equal to the Fermi-Dirac one with a small change. We also linearize the system with respect to the external velocity field. So we assume that we're driving the system very weakly. And since we're interested in the shear viscosity, we have a transverse velocity field. So as I mentioned, if the velocity is changing in one direction, the velocity field is oriented perpendicular to that. Now, what we do is a technique that my collaborators helped develop in recent years, which is use a temperature-dependent mode expansion of the kinetic theory. So we assume that this change in the distribution function can be expanded in terms of a set of orthogonal modes, but we have to define those modes for each value of beta mu. And once we do that, well, again, I won't go into the specifics, but we can turn this whole kinetic theory into basically a glorified matrix problem. So this is just a giant matrix that describes the streaming part and the collision integral. we have our expansion coefficient Cn, and this vector over here describes the driving due to this external field. So this is just a matrix problem. A matrix times a vector is equal to a vector. We can, I should say that the biggest problem is just defining the matrix here. But once you have the matrix, you invert it, and then that gives you these expansion coefficients, and that gives us complete access to this quantity here. And we can use that quantity to calculate linear response quantities like the shear viscosity. So to do that, we calculate this off diagonal element of the stress tensor, which is defined here. And it is actually defined in terms of the shear, or I should say the result is shown here. And it defines the shear viscosity spectral function at finite frequency and momenta. So this is what we do. Now I'm going to quickly leave this aside and go straight to the results for the shear viscosity spectral function and the quadrupole damping rate. So here are the results for the shear viscosity spectral function on a color plot with essentially frequency omega and momentum q in thermal units. Now, again, q and omega are not arbitrary, but they're actually related to one another. And they're fixed by the trap frequency and the number of atoms. So really, when we fix the number of atoms, the damping rate is essentially a single path here in phase space, which we can achieve by changing the harmonic trapping potential. Now, I should mention that this should be contrasted to the hydrodynamic prediction, which is essentially this horizontal axis here. And for the theorists in the room, I have a small caveat, which is that in this hydrodynamic limit shown here, this can actually access the collisionless regime as well. But you can think of this as the calculations that one would do without knowing the presence of this odd-even effect. So the typical transport. Now, in the next few slides, I will show you basically this following measure of the deviation from hydrodynamic prediction. It's the ratio of the damping rates as we calculate using this formula here compared to the hydrodynamic predictions. If this ratio is equal to 1, we're in the hydrodynamic limit. There's no difference from the hydrodynamic prediction. If it deviates from 1, then there's some signature of this odd-even effect. So here's the results for this ratio as a function of harmonic trapping frequency for fixed number of atoms n and various interaction strengths here. To remind you, this is all on the BCS side where the interactions are attractive. And the smaller the number, the more strongly the system is interacting. As you can see here, when the trap is either very tight or very flat, we actually recover hydrodynamic flow. However, for intermediate traps, we can see a strong enhancement of the damping rate as compared to hydrodynamic predictions. And in fact, this can become even more significant when we reduce the interaction strength. So in other words, being closer to the weakly interacting limit, we see a stronger effect in this case. To make this a little bit more clear, here's the ratio again as a function of interaction strength for various harmonic trapping frequencies. And I would like to note that the value of these harmonic trapping frequencies are actually out here, kind of in this tail, where you see less of a pronounced effect. But it's interestingly enough that this less of a pronounced region can still lead to almost like a 40% increase here for this type of blue parameter. Yeah. And if we go towards the hydrodynamic limit, you see that it actually vanishes as well. So really, this is, again, what I talked about before, where we can change the interaction strength to tune this thing. Finally, I'd just like to note that with the number of atoms, you can see that essentially we also recover hydrodynamics in very large clouds. So if n is on the order of 10 to the 5 or 10 to the 6, essentially we have a very small impact from this. Well, there's no presence of the odd-even effect. We have hydrodynamic flow. And for very smaller atom numbers, we can actually see still a nice enhancement here. Now, I'd like to conclude by actually telling you about previous results. This is something that actually has been done before. People have looked at the quadrupole mode and the damping of this mode. This was done in 2012 by Michael Koh. So here is the quadrupole mode frequency as a function of interaction strength on this BCS side. And you have the damping rate shown here. Now, the interesting thing about this is that they were able to extract the damping rate as a function of temperature. And essentially, this alpha is the integrated shear viscosity spectral function. And the dashed lines here correspond to essentially different, or the theoretical predictions calculated using hydrodynamic theory, and it fits the experiment quite well in this case. So I spent you the whole last 45 minutes or so telling you about the fact that this should not work in some cases. So why does it work here? Well, it turns out that the number of atoms in this case is about right, 4 times 10 to the 3, but the temperature was too hot. So around T over TF was about 0.3 to 0.5. And if you plug that into this plot, you're sitting around up here, which is exactly where you don't expect the odd even effect to occur. So really our hypothesis was that, you know, if you were able to redo the experiment, but haven't managed to cool the gas even further, you should be able to observe this anomalous enhancement of the damping rate of the quadrupole mode. So in conclusion, I would like to say that in this talk, we discussed scattering and transport in 2D Fermi liquids, and in particular Fermi gases. And we showed that at least the physics here is richer than one once previously thought. There's a new tomographic regime that can emerge, which is due to this odd-even effect, and can alter the transport properties of the system, in particular, transverse dynamics. So for the case of quantum gases, this led to an anomalous enhancement of the damping rate of the quadrupole mode, which is something that one can do in experiments. But one good thing about full gases is that this effect can be tunable across the BCS-BEC crossover, which is something that we can't really do in condensed matter materials. And the last thing, which is I would like to say that probably the biggest message for the experimentalists in the room, is that this is possibly achievable with current generation of atomic gases experiments, or let's say next generation. It probably does take a little bit of work to cool it down or to try to find the right balance of temperature and interaction strength. So with that, I would like to say thank you very much for your attention. Again, the archive manuscript is here if you're very interested, and I'll be happy to answer any questions. So thank you very much.
Thank you, Ben, so much for your great talk. We started about 5 minutes late because of technical difficulties, so I hope people are okay if we go 5 or 10 minutes over for questions. Does anyone have any questions for the speaker?
Yes.
Oh, sorry, we are recording this, so do you mind speaking the question this way?
Thanks for the nice talk. I think you already maybe went over this, but could you explain the intuition why the quadrupolar moment should be sensitive to the odd-even effect?
Essentially, it's because it's related to the shear viscosity spectral function. So if I go back here, so the shear viscosity spectral just the shear viscosity in general measures essentially, you can think of it, the response of the fluid to a velocity field that's, let's say, oriented in one direction and propagating in another. So in this case, it is what we would call like a transverse probe of the dynamics. This is in contrast to other, let's say, probes, more like longitudinal probes, like, let's say, conductivity and the like. So here, the fact we were inspired by the previous studies that showed that, again, the shear viscosity develops in anomalies. But again, people in the atomic gas world have been measuring shear viscosities for a very long time using this exact method. They take a quantum gas, they put in a harmonic trap, they excite this mode, then the damping rate gives you access to the shear viscosity. At least for a harmonic trapped gas, it gives you access usually not to the shear viscosity, but to the integrated shear viscosity over position. However, there are recent experiments in box traps that can get around this. So this is really, the reason why we examined this one in particular. Yes.
I'm still suspecting I'm missing something basic here. So you see an enhanced decay rate of the quadrupole mode. Should I interpret that as being enhanced decay of this even mode? When you say the odd even effect, I guess what's confusing me is, do you need to know anything about the odd modes if you're just discussing the decay of the even mode? Or are you just saying, look, we found that even modes decay quickly, which is interesting in its own right?
Let me just think about that for a second. Well, I hope I'll be answering this question correctly. But one thing is, I was kind of careful, if you don't mind me going on a small diatribe. No, because the thing is, if you have in the zero momentum limit, one can show that the shear viscosity spectral function is actually dominated entirely by these even modes. Okay, so at zero momentum, doesn't matter what frequency, you only this guy is only dominated by an even parity scattering rate. So if I go back to this formula, what I could do is I could replace this gamma eta by gamma E. So that's what one can do. But when you work at finite momenta, which we argue is the case that you in the harmonic traps, what you see is that there actually is a dependence on gamma odd. So this is a very toy model, and you can actually see that from here. So in other words, if Q times this C is very large, then I just put that in here. And then there's now a dependence, not just on the odd parity or even parity mode, but the odd one as well. So now in the kinetic theory, the numerical results I described, I would say argue it's maybe a little hard to see it, but in this toy model, which is a that's a little harsh of me to say, but this is essentially, you could think of this as kind of this result came from kind of like a relaxation time approximation, where you assume that every angular harmonic has a different decay rate. Well, actually two, the odd and even. And once you do that, you can see that this dependence here. So in our numerical work, we kind of can discuss this exact piece, but again, we attribute the effects of the finite momenta to this odd even effect and the anomalously long-lived odd parity modes. Yes.
On where we can put in the box.
This probably goes away. Either that or it depends on the size of the box. So the key thing here is that, again, this effect needs a finite momentum. And if you put it in a box, then the box size will be or the inverse of the box size will be your momenta. And again, if the box is too big, then you have hydrodynamics. If the box is too small, maybe I have a suspicion you also don't see this because there's not enough, everything's kind of, let's say, in the ground state or something. So, yes. So you have to fine tune. Yeah.
In your plot of like the shear viscosity versus the frequency, is there any, like, it kind of looks like it's like the different interaction space, it's like one fourth certain feet, like frequency value. Is there anything significant about like the frequency where it peaks at?
I need to check that. That is something we haven't addressed as much, but yeah, that would be actually, I will look into that for you. Yeah. Sorry, I don't have a good answer for that. Yes. You first. Yes. Yes.
Oh, maybe, yeah, this is outside the field, but so if you have a condensed matter system, is this effect visible? Like, what experimental situation would you need to set up?
So that was this case. So here, this experimental paper, what they did was they created rings of monolayer and bilayer graphene. And I don't fully understand exactly what they did, but they were able to basically extract the, like, let's say the impurity scattering rate, and then also this kind of viscosity contribution. It was some fitting of the data. I would highly recommend that you read this paper to get the exact details. But what the key thing is that they obtained this prediction for this shear viscosity divided by the density. And if you actually assume that there's this odd even effect present, then you naturally get this 1/T. So that's what they really tried to claim here, was that you have this nice 1/temperature dependence for both monolayer and bilayer graphene. Here, these other lines correspond to other types of, so this is T squared, 1/T squared. So here, really, their claim was that, okay, here's a prediction for the odd even effect. It's this 1/T. This is obviously 1/T. It's not 1/T squared or anything else. That was their smoking gun for this. Yeah. Yes.
I guess I see those other
I mean, the benefit of, I would say, condensed matter platforms is that, like, I mean, compared to our experiments that we worked on, these are super cold. Like condensed matter. I mean, atomic gases are probably very hot in comparison. But the benefit that you have here is that we can at least push it into a regime where we should start to see it. And then we can kind of change the interaction strength, and we have other parameters that we can tune in comparison to these nice people. Yeah. Yes.
Yeah, I just have a question, I guess, about like, as someone who doesn't work in 2D system, is like point one particular temperature like easily attainable?
Well, I could say that this experiment did, so this one. But I imagine that I mean, that was something that maybe we should all in Joseph's lab chat about. But I would say that it's possible, but I agree that the key stumbling block for seeing this experimentally would be trying to cool it and also not making sure that's not in a superfluid state. So there's again probably some balancing of interaction strength and temperature and what can be achieved. And that would be that's probably the main technical challenge for this.
Okay, are there any further questions for our speaker? Seeing none, let's thank Jeff Maki again for his wonderful talk.